Hi, thank you. And this is the case study that we will show you from the point of view of a civil engineering firm. So this is one of hundreds of railway bridges that we need to assess and retrofit any given year. And I'm a civil engineer, and with me is the technical director of that engineering that is also helping us with these assessments. So the general outline of the presentation will be, first we will show you the overview, the general case study, then we will jump to the assessment of the vulnerability, and then on the basis of what's shown in Chapter 1 and in Chapter 2, we'll be going through the design phase of the retrofit. So this is the overview, the subtext being a tricky situation, as this is a small bridge, maybe not the most landscape worthy, but it carries a lot of little details that make the problem. The real idea here is to show you that the boundary condition make the problem. As you can see from the pictures, there is a huge backfill standing on top of the arch. This makes already a suggestion that in the retrofit a top-down approach is less probable. And there is a very small loading gauge for the road passing through, so also the classic massive approach for the retrofit would basically seal shut the traffic, and being this very hilly part of Italy would mean closing one of the few roads crossing the tracks in this area. Moreover, the bridge width is much greater than the bridge span, and this will be accounted for both in the modeling and in the retrofit. One other boundary condition is that no railway traffic were to be allowed during the retrofit. So let's look at the assessment that was carried out in maybe 2019. It was a pushover analysis for global vulnerability, where there was a 2D model being carried out that is an allowable hypothesis for a bridge having a much smaller span rather than width. Whereas for the linear kinematic analysis, it was carried out for the spandrel tipping vulnerability. Having not studied the backfill, no mechanical characterization, the backfill was considered purely as mass, and this for sure is a very safe assumption, but was the only one maybe available at the moment. And a word has to be said about the soil-structure interaction, which maybe yesterday we've seen some glimpses. But I consider maybe the biggest topic to discover, and hopefully the next workshop will go throughout the whole thing. For this particular structure, it was agreed upon for a typical approach, which is the complete restraint, maybe 1 meter under the walking plane of the road passing through, to account for the terrain contributing to the restraint of the structure. For sure, this will have quite the importance in the results. Looking at the results, firstly at the pushover curves, we see that some, even though the structure is itself quite rigid, there is some ductility shown. The pushover was stopped due to the compressive strain limit being met, and this for sure, as we said before, is heavily influenced by the soil structure interaction hypothesis. There is some opening, hinge opening at the bottom of the abutments and some on the arch, but it's the abutments that make the problem, let's say, of the vulnerability. Whereas for the local spandrel tipping, the huge backfill pressure causes the vulnerability. So all in all, let's take a look at what was hypothesized in the retrofit, taking into account what we've shown as Chapter 1 and Chapter 2. So for the seismic retrofit, the global behavior, the chosen idea was a very thin layer of fiber-reinforced cementitious grout in the introdos, not to still shut the road passing through. The particular grout characteristics are fluid and high great ductility with great compressive and tensile strength. Moreover, it has a great grip strength to allow good interface, interlocking masonry and grout, but still the steel connectors were put into place. So let's look firstly at the pushover curve, so we can see much greater ductility achieved, and looking at the behavior of the bridge, we see that there is a hinge spread thanks to the effect of the grout. This hinge spread allows for less concentration of the compressive strain, which again is the criterion stop of the pushover curve. And all in all, a greater push is allowed thanks to this, and the retrofit is achieved. For the local spandrel, again, being the bridge very wide and with a great terrain, part of terrain standing on top of it, the backfill being huge, we couldn't do the classic solution, which is basically a chain going from one side to the other of the bridge. So we had to maybe borrow an idea from the geotechnical world, being self-drilling bars with continuous thread that, thanks to the cementitious injection, can resist the tipping and can be easily accounted for in the kinematic assessment of the vulnerability and then the retrofit. The main checks that need to be carried out are the extraction of the bars and the yielding of the bars, but having no terrain characterization, there is a need for an empirical approach with in situ testing to make sure that the hypothesis used for the resistance of the bar to extraction finds perfect match with the reality of the case. And as you can see, the steel bars are put at an angle on the bottom right picture in order to avoid the structural part of the arch. So with this case study, we've shown a small, simple, maybe easily forgettable arch that had no simple solution and no typical solution available, and still had a lot of thought need to be put into it. So thank you for the attention. These are our email, and if you scan the QR code, you will find the email saved.